So in this lesson, we're going to take a look at how we evaluate logarithms. So our first step is to figure out what is a logarithm, and then the second part of the note we'll look at how we actually evaluate them. The first step in the process then would be to go back and look at, well, what is an exponential function? So remember that an exponential function calculates the power given the exponent. So for example, something like this here, y equals 5 to the exponent x. The idea here is that we are given the exponent. In other words, that is our input variable, x. So given that exponent, we will then calculate the power. In other words, that is our output variable. So our output is the answer to this power. So there is our output, which is the power that we are calculating. For example, if x is 3 as our input, then our output would be the value of that power. So 5 to the exponent 3, or y would be equal to 125. Now, to come up with the idea of a logarithm, what we need to remember here is that what is an inverse function? Logarithms are the inverse of the exponential function. So the first thing we need to remember is that to get an inverse, what we do is that we switch the x and the y values. Notice that as we do that, we are now given the power. So our input variable is now the actual power. And our output variable now, as we switch them, our output will be to figure out what is the exponent. In other words, our question now would look more like this here, where we say if x is 25, then we have given the value of the power, 25, and our goal then would be to calculate the output, the y value, which is the exponent. In this case, by observation, we would be able to say, well, I know that y must be 2, since y squared gives us 25. However, for any function, when we write a function, we typically don't want our output variable someplace in the calculation. What we want is our output variable, like our exponential function, to be isolated. So that's our next goal then, is to say, well, how would I then isolate that output variable y? To do that, what we have to do mathematically is define this function. So there's no way that we can just rearrange the equation to isolate for y here. So in math, we define a new function which represents the opposite of the exponential function, or the inverse of that exponential function. So here's how that looks. We would say, well, the logarithmic function is going to calculate that exponent. So if I want to isolate y, what we do is we rewrite this in this way. Y equals, and here's the definition of our new function, log base 5 of x. In words, I would read this as log base 5 of x, or sometimes this is also read as log x base 5. If we notice where all the pieces move as we do this, notice that the output variable is the exponent. Well, that is now the answer here that has been isolated. So there is our exponent. We call this piece here the base of the power. This is also called the base of the logarithm. So the base still stays the same. The base of the power becomes the base of the logarithm. And then lastly, our x value inside the logarithm here or at the start of our equation over here. On this side, we would say that this is the value of the power. That is the answer to 5 to the exponent y, so that's our power. So x is representing the value of the power. On this side, we give it a new name. We say that that x value is called the argument of the logarithm. So our first step here is just to try to work here then between these two forms. Okay? We call this here our logarithmic form. Sorry, this whole piece, we call this our logarithmic form. The idea then would be, well, what does this look like in its exponential form? How do I write this as a power? Okay, so there's our exponential form and our logarithmic form. So if I want to do that, what I normally start with is this piece here, because the base, notice it's the base for the logarithm, it's also the base for the power. So I'm going to start with the base is 3. The answer to a logarithm, so the answer to this logarithm is the exponent. So the answer to the logarithm must be the exponent. So this is 3 to the exponent 4 equals, and then the only piece that is left here is the argument, and the argument is what becomes our power. The argument on this side is the power, the value of that power on this side here. If we take a look at a second one, we can do the same thing here. We would say that the base is 25, so that's where I'm going to start. The answer to the logarithm is the exponent, so 25 to the exponent 1/2 equals, and the answer to the power is the argument here. So 25 to the exponent 1/2 equals 5. The nice part is that we can actually verify, does this make sense, right? Does 3 to the exponent 4 equal 81? Okay, quickly we can check that yes, that is true. And the same thing here, 25 to the exponent 1/2, does that equal 5? And again, quickly we can check that that's true. Reminder here that an exponent 1/2 is the same as doing the square root of 25. We can also now do this in the opposite direction. So we can now say, well, if I start in its exponential form, can I write this in its logarithmic form? And I'm going to do the same thing. The easiest place for me to start is that base. So the base of the power becomes the base of the logarithm. So log base 2. The argument is the answer to the power. So log base 2 of 16 equals our exponent. The answer to the logarithm is the exponent. I can do the same with this here. The base this time is 1/2. So log base 1/2. Next is the answer to the power is the argument, and the answer to the logarithm is the exponent. So there it is in its logarithmic form. Last one, we'll do one more, and there's a little bit that goes with this one. So same idea, log, the base is 10. The argument is the power, so that is the 10,000. And the answer to the logarithm is the exponent. So there it is in its logarithmic form. Now, this is an interesting one because I can actually write this a different way here as well. In this case, I can also say that this is log of 10,000 equals 4. If you go to your calculator, you'll see that sometimes your log button on your calculator doesn't have a base that is written, and that's because we call this one here the common logarithm. In the common logarithm, the base 10 is implied. So in general, our logarithmic function then starts from the inverse of the exponential function So by switching the x and the y, and then we can rewrite this and say that we end up with the exponent is equal to log base b of x. There's a couple conditions on this function. The first is with that base number. For that base number, we say that it has to be a positive number. So the base has to be a number greater than 0. Okay? And it also wouldn't make sense if this base number was 1. I don't really write powers of 1. So we also say here that it must be greater than 0, but we also say that it cannot equal 1. There's also then, as we talk about a function, some restriction on the domain, which is our x values. Keep in mind that in this case, the answer to a power, okay, that this answer x will always have some positive value. Okay, if I say that the base is restricted to positive numbers only, then the answer to the power must also be positive. So we say here then that the domain is x greater than 0. So the base and the x value both have to be greater than 0, and the base is not allowed to equal 1. We can now flip the page and we can use that to actually solve some equations. So in this case here, I want to know, well, what's the argument here that will make this true? And some of you might be able to see by observation what would have to be here. An easy way, though, to do this is to switch this to its exponential form. So if I switch here to exponential form, again, I start with that base. The base is 2. The answer to the logarithm is the exponent, and that equals the argument. And notice by switching from logarithmic to exponential form, this becomes a really easy equation to solve. We end up with that x is 32. We can also do this when the base is the exponent here by switching this to its exponential form. So the base is x. The answer to the logarithm is the exponent, and that power equals the argument 81. We can then solve for x by taking the square root of both sides. Normally we would say that this is plus or minus the square root, but remember x here is the base, and since we are solving for the base, we have to remember that from what we just talked about, that the base will always be greater than 0. In other words, that we will not have the plus minus here. It can only be a positive answer since it's the base of that logarithm. This gives you an idea a little bit about what logarithms look like and how we come up with the logarithmic function. The last part of the note now, I want to spend some time looking at, well, how do I actually evaluate then a logarithm? So what we need to understand here then is that logarithms are the inverse of the exponential function. In other words, we are trying to figure out, in this case here, if I'm evaluating this logarithm, I'm trying to figure out the exponent that I would need, right? We can see this here. What exponent do I need to come up with this argument of x? So to solve a logarithm is really asking this question here. It's saying 5 with what exponent? Okay, there's our base, 5. 5 with what exponent will give us an answer of 125. As a logarithm, we can actually write this and say log base 5. We're saying 5 with what exponent will give us 125. In this case, by observation, we can see that the exponent must be 3. So that is the answer to our logarithm. The answer is the exponent that we would need to write 125 as a power of 5. The next question, we're basically doing the same thing. We're saying, okay, if my base is 7, how do I write then 7 as some power to equal 1? 7 to the exponent, what will give us 1? As a logarithm, then I could write this as log base 7 of 7 with what exponent. So this is where we have to now think about our exponent rules and think, well, what kind of exponent could I put on 7 to give us 1? And this is where we need to catch then that, remember, anything to the exponent 0 gives us a value of 1. So we end up here with an answer of 0. Notice that our goal here then is to try and have these things have the same base. If they have the same base, the answer is just the exponent. If we try the next one, we end up with the same scenario. We're trying to figure out, how do I write 1/8 as a power of 2? In other words, 2 with what exponent is going to give us 1/8? What we need to think here then is, how do I get fractions? And this is where then, with our exponent rules, we need to remember that this would actually come from a negative exponent. As a logarithm then, we could write log base 2. How do I write 1/8 as a power of 2? I do that with an exponent -3. The negative would flip that over and make a fraction. 2 cubed would give us the 8. In other words, as soon as our base is the same, our answer is that exponent. So our answer here then would be -3. One that can be a little bit trickier is what happens when now all of a sudden the base is larger than the argument. It's the same question. We're still asking then, how do I write 3 as a power of 9? So 9 with what exponent will give me 3? Or as a logarithm, we can say log base 9 of 9. What exponent do we need on that 9 to make the 3? What we need to remember here is that the connection here is that the square root of 9 is equal to 3. Or as an exponent, that would be 9 to the exponent 1/2 equals 3. In other words, the exponent that we need is 1/2. So this is where we need to remember all of our exponent rules, where we have potentially exponents 0, we have negative exponents, or in this case now, we have a fraction exponent. In E, we have a little bit of work here, because now I have the 4th root of 8, and somehow I'm trying to write that as a power of 2. The first thing I'm going to do is write the argument as its exponential form. So right now the base is 8, and we got to remember that that radical I can rewrite as exponent 1/4. I'm then going to focus on, I want to write that 8 as a power of 2. So can we write 8 as a power of 2? Hopefully we see that yes, we can. We can rewrite the 8 as 2 cubed, and we still have that exponent 1/4. We can now use our exponent laws, which say I can multiply those two exponents together, and we would then have the same base here. So our final answer then will be 3/4. We can also work on combining this together into a larger question where we now have two logarithms that we are going to add together. So if I break this apart and just look at the first one, I can say, how do I write 49 as a power of 7? So I can do that with an exponent of 2. And the second one is saying, well, how do I write 5 as a power with a base of 25? And again, this is where we have to realize what exponent, what would you do to the 25 to get 5? The answer here is that I would need then an exponent of 1/2. I would need to take the square root of that. So our answer here then would be 2 from the first logarithm plus 1/2 from our second logarithm. And then we can simplify by adding these together. If I get a common denominator of 2, I would have 4 over 2 plus 1/2, which gives us an answer of 5/2.
Please call 5308, Mrs. King, 5308.
Now, this next one is quite a tricky one. I'm going to show you where our answer comes from, and then I'm going to show you a bit of a shortcut that we could try to use here as well. The first thing I'm going to realize is that I am trying to write here 32 as a power of 4. That's my ultimate goal. My problem is that 32 does not write as a power of 4 using any of our simple rules that we've looked at so far. So when that happens, what I'm going to suggest is that since the base 4 is not easy, that what we're going to do is we're going to just try any base. Can I rewrite 32 as a base with any power? This is where you do need to know your powers well so that I can recognize here that yes, I could actually write that as a power of 2. This is 2 to the exponent 5. Well, that helps us because now what I can do is I can now compare my base 4 with the new base here, and hopefully we realize that, hey, I can write this 2 as a power of 4 using a fraction exponent. I can say that 4 to the exponent 1/2, the square root of 4 is equal to 2, and this whole thing is to the exponent 5. And then as we saw in an example previously, we now have the same base, so my answer is 5/2. Now, that can seem quite complicated to do, so here is a trick that kind of gets around that problem if we're really stuck on a question like this. I'm just going to say on the side that here's a neat trick that you can use to get that answer. So if I rewrite the question, log base 4 of 32. When I'm having trouble matching these two up to try to write 32 as a power of 4, what I'm going to do is look at both of these at the same time. And it's almost like we're doing a change of base. Can I write those both, the base and the argument, as a power with the same base? Hopefully we recognize that those are both powers of 2. So I could rewrite this as log, and instead of writing 4, I'm going to rewrite the base as 2 squared, and the 32 I'm going to change to the same base. Notice that our answer of 5/2 now is presented to us if we know where we are looking. The answer ends up being the exponent here and the exponent here. And if we put those two together, this neat trick gives us that answer to a question that is otherwise can be quite difficult to find the answer here. So our trick is that we are going to take this and we are going to write the base and the argument with the same base. Notice that that trick would also work up here as well. If we try that trick on this question here, we could have actually back here said that this was log base 3 squared, and this is 3 to the exponent 1. And if I use that same idea, we would then have the exponent here and the exponent here gives us our answer. So if you're having trouble sometimes spotting that, how do I write 3 as a power of 9 using fraction exponents? An alternate way we can get around that is to try and write the argument and the base using a base that is the same, and we can actually get our answer to the logarithm by taking these two exponents and putting them together in a fraction. Okay, last one, and all of a sudden the question looks very different here for these last two parts. Similar to each other, but different. So I'm going to use the first one to try and explain where this answer comes from, and then we'll create a rule that allows us to answer the second one much easier. So in this case here, I'm going to start with that exponent and say, well, I'm trying to evaluate a logarithm, so I am trying to then write 36 as a power with base 6. And hopefully we see that we can do that easily by writing 6 squared. So if I now evaluate this logarithm, they have the same base, so my answer then is 2. So here we have 6 squared. And if I do 6 squared, we get 36. Now notice the original question, where did the 36 come from? Well, the 36 is the argument here, and there is our answer. And that happens because these are the same base. What we need to remember here is that when you have the inverse of a function, so we have the exponential function and we have the logarithmic function, if I put one inside the other, these will undo each other, and we simply end up with our answer here of x. So our inverse functions essentially cancel each other out. So I can then apply that technique here where I see I have a logarithmic function, base 9, that is written inside as the exponent of an exponential function, base 9. If those two bases match, then those two functions will cancel each other out, and our answer is just the argument, the same that it was in our previous question. There's lots of new ideas there to try with this idea of a logarithmic function, okay, starting with where it comes from, so some of our theory, the idea that we can switch between its exponential and its logarithmic form, and then lastly, this idea of how we evaluate logarithms. There's practice posted, so please take a look at the practice questions and see if you can figure out how to evaluate these logarithms. Have a good day.